So we are just going to solve questions in gym. A series of questions compiled in order to get yourself prepared for the end of the next exam. So start. Let's go ahead and start. Let's go ahead and start. So these are basically the questions from your slides and some past questions as well. So we start with the basics. And when we start with the basics, then we build up from there as well. All right. Adding. First of all, let's start solving some questions on stresses. Yeah, stresses in soil, vertical stresses in soil. So stress. We are going to start solving some questions under stress. I think that will be cool. So let's start with the basics. So, but before that, let me talk about certain things you should know. So under stress is basically what you are supposed to take note of will be the total stress, the total vertical stress. You should also take notes of pore water pressure, and you should also take notes of effective stress. Check that out. So let's start. So for the first question, we have a simple basic diagram, right? A simple basic diagram. Let's assume this is a stress soil sample. So from here we have 5 meters, and we have the unit weight of this soil to be 18 kilonewton per meter cube. We are being asked to find the total stress. Okay, so in this one, we are just asked to find the total vertical stress of the soil. So the total vertical stress. Now, let's come back here. To find the total vertical stress is just represented by sigma, and this is equal to the unit weight of the soil times the specific distance. The pore water pressure is also giving us the unit weight of water times distance, the depth as well, and the effective stress is simply giving us the total vertical stress minus the pore water pressure. So in this question, since we are asked to find just the total vertical stress, we are simply just going to state that the total vertical stress is equal to the unit weight times distance. And this is simply going to give us what 18 by 5. Then that will give us 90 kilonewton per meter squared or 90 kilopascal. Quite simple. Let's take the second model. So there's one. Let's take the second model. Now, in here we have two soil samples, two soil layers. So with the soil layer above, we have a distance of a thickness of 2 meters, and over here we have 5 meters. Okay, let's do it this way instead. So over here we have 2 meters distance. Then down from the top to the side, we have 5 meters distance. We are saying that the unit weight of the soil above, it's 16 kilonewton per meter cube. And the unit weight of the soil below that's saturated, we have 18 kilonewton per meter cube. In here also, we have the water table. So this symbol is simply, when you see this symbol, it simply means water table, meaning that the soil above is saturated, meaning that the soil, the water in the soil starts from that particular level. Right. So in this question, we are being asked to determine the vertical stress on the soil at a depth of at a depth of z equals 5 meters. So just the total stress. We are being asked to determine the total stress at this depth. Just the total stress. Now, in order to find the total stress, again, you know that the formula is simply the unit weight times the distance. So over here we have for the soil layer above, we have what? The unit weight, which is 16, times the distance of what? 2 meters. Plus, then you come down to the soil layer below, unit weight of 18 times what distance? The distance is supposed to be for this second layer, but we know that from here to here is 2, and from here to here is 5. So we simply have what? 5 minus 2. And this is simply going to give us 86 kilonewton per meter squared, or somebody will also say 86 kilopascal. That's for the total vertical stress. Now, if you want to find the pore water pressure in this question, the pore water pressure is simply giving us the unit weight of water times the distance from where the water table is present to your point of interest. So over here, so with this section, the unit weight of water is going to be giving us 10 kilonewton per meter cube, unless otherwise stated. So you should be checking. In other instances, you'll be giving 9.81 kilonewton per meter cube. So you should be checking that, right? So let's say over here, I want to use 10 kilonewton per meter cube. So if I want to find the pore water pressure at, let's say, this same distance, A, the pore water pressure is simply going to be 10, the unit weight, 10. So we have unit weight times distance. So 10 by a certain distance. And that distance is the distance from the water table to your choice of your distance of interest, which is from this side to this side. And that's what? 3. So we are going to get what? 30 kilonewton per meter squared. Let's take our third model. So in here, so we also have two soil layers. We have for the first layer, we have a distance of 3 meters, and for the second layer, we have a distance of 5 meters. We have a distance of 3.5 meters for the second layer. So we are considering the top layer to be sand with a unit weight of 18 kilonewton per meter cube. Then we are considering the lower soil to be clay with a unit weight of 19 kilonewton per meter cube. Now, we are being asked to determine the vertical stress at point A. And this point A, the vertical stress. So we know that the vertical stress is simply gamma z. We've been doing this for quite a long time. So we simply have this side, the vertical stress over here plus the vertical stress over here. So we know that the formula is unit weight times z. So the unit weight of this soil times the distance, the depth of the soil. So we have the unit weight to be 18 times the depth, which is 3. Plus, we come to the second layer. The unit weight is what? 19 times the depth, which is 3.5. Then we go ahead and compute this. We will have 120.5 kilopascal or 120.5 kilonewton per meter square. They are still the same thing. Okay, let's keep advancing. Let's take our fifth model. So in this model, we have 3 soil layers. 3 soil layers. Now the distance, the depth of each layer, the boundaries of each layer is given below, is given us So in here we have 2 meters, 2 meters, we have 3 meters. We are being asked to determine the stresses at point A. We are also told that the soil here has a unit weight of 18 kilonewton per meter cube. The soil here has a unit weight of a saturated unit weight of 19 kilonewton per meter cube. Then the soil below has a unit also saturated 20 kilonewton per meter cube. Right. So meaning that since we can, and then we have a water table here. So all the soil beneath the water table will have a saturated unit weight because of the presence of water. So we are being asked to determine the total vertical stress, which is given as sigma. We are being asked to find the pore water pressure, which is represented as U. And we are also being asked to find the effective stress. We are also being asked to find the effective stress, which is given as sigma prime. Right. So now let's begin. In order to find the total stress we all know is given as gamma z, right? So how do we go about this? We are going to find the total stress for each soil layer, the sum. So for the first soil layer, we have a unit weight of 18 and a depth of what? 2 meters. So we are simply going to get 18 times 2 plus, we do same for this side. A unit weight of 19, a depth of 2. So 19 times 2 plus, we do that for the last layer, so 20 by 3. And this is simply going to give us 134 kilonewton per meter square. Now, pore water pressure. The pore water pressure is simply given as the unit weight of water times the depth. So what's the unit weight of water? For this particular tutorial, I said we are going to be using 10 kilonewton per meter square, unless otherwise stated. So we have 10 by the depth to the point of interest. So the point of interest is at A. So from where the water table is located to A, meaning that from here to here, what distance do we have? We have a distance of 2 plus 3, which is 5 meters. 5 meters. So simply we are going to get 10 by 5, and that will give us 50 kilonewton per meter square. Then we have to find the effective stress. The effective stress is simply given as the total stress minus pore water pressure. The total stress being 134 minus pore water pressure being 50. They are going to get 84 kilonewton per meter square. The sound low. So we are going to take our fifth layer. We're going to take our fifth layer. So this is our fifth layer. We have a distance 3 meters. We have a distance of 4 meters. And we have a distance of 3 meters over here. So we are being told this is a field that has a unit weight of 19 kilonewton per meter cube. We are being told consider this side as clay, having a saturated unit weight of 19 kilonewton per meter cube. This is sand for a saturated unit weight of 20 kilonewton per meter cube. Alright. Mind you, this is the distance between the middle of the sun and this is also the middle of the clay. We have our water table here. That's why all the soils above has a saturated unit weight. Alright. Now, we are to determine the total stress, the pore water pressure, and the effective stress in the middle of the clay and sand. So, in the middle of clay and sand. Alright. So let's begin. But we have certain conditions. The first condition, we are to find these parameters in the middle of the clay and sand. But the first condition says that before construction of embankments. So before construction of embankments. The second condition says immediately after the construction. Immediately after the construction of the embankments. And the third condition says that several years, so we are supposed to find this several years after the construction of the embankment. Take note of this question very well. So these are the three conditions. We are going to consider these three conditions in finding the total stress, the pore water pressure, and the effective stress in the middle of the clay as well as in the middle of the sand. So let's begin. So let's start with in the middle of the clay. In the middle of clay. So let me just call this one as let me question A, B, and C. So in the middle of the clay, question A, we are supposed to find these three parameters, the total stress, pore water pressure, and effective stress before the construction of the embankment. So this field is the embankment, right? This field is the embankment. So we are assuming before construction, we are assuming that this layer, which is the fill layer, is not present. So if the fill layer is not present, we're having something more like two layers this way, where we have clay here and we have sand here. That's how you're supposed to consider it. So from here to here is simply going to be 4 meters. From here to here is simply going to be 3 meters, right? If that's before construction of the embankment. So if you are finding this in the middle of the clay layer, meaning that we have a distance of 2 meters here, 2 meters here. Then we have our water table present here this way. So in so doing, if you want to find the total vertical stress in the middle of the clay layer, it's simply from the ground surface to the middle of the clay. So we are going to simply have the unit weight of the clay, which is 19, by the distance to the point of interest, which is the middle of the clay layer, so 2 meters. And this is going to give us 38 kilonewton per meter square. Right. Now the next thing is to find pore water pressure again in the middle of the clay layer. That's also under the same condition before the construction of the embankment. So what this means is that again the pore water pressure, we know that the pore water pressure is simply the unit weight of water times a certain distance. So we are going to say that the pore water pressure is simply going to be the unit weight, which I said we are considering as 10 times the distance, which is from this side to this side, again 2 meters. And that's going to give us 20 kilonewton per meter square. Now let's find the effective. So over here we can simply go ahead and find the effective. You know that the effective is simply the total minus the pour water. So we have 38 minus 20, and that's going to give us 18 kilonewton per meter square. So this the conditions under in the middle of the clay layer for A, which is immediately after the construction of the embankment. Now, if you want to consider this before construction of the embankment, yeah. So A before construction of the embankment. So let me just say, yeah, A before construction of the embankment. Now, under same condition, we want to consider immediately after the construction of the embankment. So immediately after construction of the embankment. So if we want to consider immediately after construction, meaning that we are just going to consider this whole, we are going to consider this whole layer, right? Everything in here. So let's say that for B, which is immediately after construction, the total stress is simply going to be from every soil layer above the point of interest, and this is the point of interest, the middle of the clay layer. So everything above it. So we are going to get 19 by 3, which is the stress for the field, plus the soil, the clay sample above the point of interest, which is this side. This side. We are going to get 19 by 2. So 19 times 3 by 19 by 2. And that's going to give us 95 kilonewton per meter square. Then our pour water pressure is simply also going to give us again from the water table to the point of interest. So we have 10 by 2 as well. And that's 20 kilonewton per meter square. Then again, you know that the effective stress is simply going to be 95 minus 20. And that's 75 kilonewton per meter square. Now, the thief aspect says several years after the construction of the embankment. What this means is that, you see, since there is poor water pressure, we are assuming that several years after the construction of the embankment, the water in the in these layers is going to drain out. That's the main reason why. So several years after the construction of the embankment, we assume that the water in this model is going to drain out. So again, if I want to find the total stress is simply going to be the level of stress above it, right? So again, we are still going to have 19 by 3 plus again 19 by 2. So 19 times 3, 19 by 2, and that's going to give us 95 kilonewton per meter square. Now, the pour water pressure. Pour water pressure in this case, since we are seeing several years after the construction of the embankment, we are assuming that pour water in this case has been sipped out, has been removed or drained out. So the pour water condition in this case is simply going to be considered as 0, right? Then the effective stress is simply going to be 95 minus 0, which is also 95 kilonewton per meter square. So take note of this condition several years after the construction of the embankment. We assume that the pour water has been spaded out. So we do not have any pour water pressure in this case. So this is the conditions for in the middle of the clay layer. Now let's consider in the middle of the sand. In the middle of the sand. So let me erase this side. In the middle of the sand. Okay. We are going to consider in the middle of the sand layer, right? In the middle of the sand. And there's the sand. So in the middle of the side. So with the same conditions, A. So before construction of the embankment, meaning that this side is not available. So we are just simply going to have a layer this way, right? Then we consider the middle. So assume the embankment is not present, right? Assuming the embankment is not present. So the total stress is simply going to be without the embankment. So 19 by 4 plus 20, which is that of the sand, times the distance to the middle. So it's 3. So we have by what? 1.5. And now we are going to get our total vertical stress. Our total vertical stress to be 106 kilonewton per meter square. So 106 kilonewton per meter square. Right. Then the pore water pressure at this point go from the water table to the middle of the sand. So we have 10 multiplying the distance from the water table to the middle of the sand. That's 4 plus 1.5. And this is simply going to give us 55 kilonewton per meter square. So we have 55 kilonewton per meter square. Then our effective stress is simply going to be what? 106 minus 55. And that's so 106 that's 51 kilonewton per meter square. So this is the for condition A. Now for condition B, which is immediately after the construction of the embankment. So this we are going to consider the embankment being present. We're going to consider the embankment being present, right? So again, under the same conditions for the construction immediately. So the total stress is quickly going to start from that of the field. So 19 by 3 plus that of the clay, which is 19 by 4 plus the sand above the points of interest. So 20 by 1.5. And this is simply going to be 153 kilonewton per meter square. So 163 kilonewton per meter square. For water pressure, 10 by the distance from the water table to that point of interest. Again, 4 plus 1.5. So 5.5, which is 55 kilonewton per meter square. Then your effective stress, 163 minus 55, which is going to be 108 kilonewton per meter square. 108 kilonewton per meter square. Now let's solve the last part of the question, which says several years after the construction of the embankment. So let me read this. Several years after the construction of the embankment. What this means, just as I explained in the first one, what this means is that there has been dissipation of pore water out of the layer. So more again, your total stress is simply going to be 19 by 3 plus 19 by 4 plus 20 by 1.5. And then simply going to be again 163 kilonewton per meter square. But since it's several years after the construction of the embankment, pore water has dissipated, and we are assuming pore water to be 0. So your effective stress is going to be 163 minus 0, which is 163 kilonewton per meter square. So this is what we are going to consider under we are going to consider under pore water pressure under stresses. This is what we are going to consider under stresses. Now let's move to phase diagram and let's see if you can have some let's understand some concepts under phase diagram as well. All right. Okay. So this we are going to consider certain aspects under phase diagram. So this is going to be our set question. So let me just go ahead and write down the necessary parameters as I read it. So a soil specimen has volume. So a soil specimen has volume 60 centimeter cube. So let me. So we've been told that the soil specimen has volume of 60 centimeter cube. So that's the total volume. Total volume of soil, 60 centimeter cube. And a mass of 110 grams. Again, we've been given a mass of cement has volume 60 centimeter cube. So that's total. Right, right. So we've been given a total mass of the soil also as 110 grams. So total mass of soil. The mass after this, the mass of the soil after oven drying is said to be 80 grams. So mass of soil after oven drying. So initially, you know that the soil will contain water. Now after oven drying, the soil is going to lose water. So mass of the soil after oven dry is simply soil, the mass of dry soil. That's what that statement is simply saying. So mass of dry soil. So the mass of dry soil is simply 80 grams. Now, assuming specific gravity of 2.71. So we have specific gravity. Okay, so let me write the parameter. So total mass of soil, which is being written as this total volume, so V, 60 centimeter cube. This total mass, so M M as 110 grams. And this is mass of dry soil. Okay, this giving us 80 grams. Now we have to assume a specific gravity. So specific gravity, which is GS, as 2.71. Calculate, so we are supposed to calculate the bulk density, which is giving us rho B. We have to calculate the water content, which is giving us W. We are also supposed to calculate the degree of saturation. Yeah, we are supposed to calculate the degree of saturation. So we are supposed to calculate the porosity, which is giving us N, and the degree of saturation. The degree of saturation. All right. So let's just begin. So, but before that, I can derive some assumptions from. So let's look at something. We've been given the total mass of the soil, the 110 grams. So you know that the mass of the soil is simply the soil. The total mass is simply that of the dry soil and the water content in it. So if the total mass is 110, then after me oven drying the soil, I'm getting a mass of 80 grams. What does that mean? It means that the amount of water in the soil was simply what 20 grams. So the mass of Though the question didn't state this, I can see that the mass of water in the soil, mass of water in the soil, it's simply going to be 110 grams, which is the total mass of the soil minus the mass of dry soil, right? And this is simply going to be 30 grams. Now again, we are supposed to consider, let me write it here, the density. We're supposed to take the density of water, rho W, as 1 gram per centimeter cube. Right. So let's begin. This phase relation is just formula work. So we can analyze the formulas and know what to do. So first of all, we are supposed to find the bulk density. So the bulk density given us rho B, it's simply the total mass of the soil over the total volume of the soil. Now, what's the total mass of the soil? The total mass of the soil is given as 110, and the total volume of the soil is given as 60. Total, the total volume of the soil is given as 60. So when we compute this, we are simply getting 1.83 grams per centimeter cube for 1.83 grams per centimeter cube. Now, so this is the bulk density. Let's go ahead and find the okay, let's go ahead and find the water content, which is given as W, small W. So let me come down. So the water content is simply the mass of water in the soil over the mass of dry soil. The mass of water over the mass of dry soil. So what's the mass of the water? The mass of the water was simply 30, and the mass of the soil is 80. So what do we have? 0.375. And you know that the water content is usually expressed as percentage. So we have 0.375 by 100%. There we are going to say that the water content in the soil is simply 37.5%. Now, the next one, oh, I forgot something here. We are supposed to find dry density as well. Dry density. So the dry density is simply the mass of the dry soil over the volume. The mass of the dry soil over the volume. So let's say, um, okay, so C, let me call that C. The dry density is simply given as rho D. So the mass of the dry soil over the total volume. And that's the mass of dry soil 80 over 60. And that's 1.33 grams per centimeter cube. Good. The next one we are supposed to find the saturated density. I think I left that one out as well. Saturated density. Now, the saturated density is simply rho sat, right? This is the saturated density. So in order for me to find the saturated density, I'm simply going to, so the saturated density is given us. Where is my, okay. The total mass of the soil, that's the mass of the soil over the volume, right? But in here, we are going to use this formula. That's the specific gravity of the soil times the density of water plus pore water pressure multiplying the density of water. All this divided by 1 plus the void ratio. So E here is the void ratio. Take note of that. So this is the formula we are going to use. Find the saturated density. Let me scroll down. So let me go. Take note of it. Take note of that formula. So this is where we are going to. So let me solve it. So the saturated is simply going to be specific gravity. We know what the specific gravity is, right? 2.71. It was given. So 2.71 times the density of water, which was given as 1 gram per centimeter, plus our void ratio, of which we do not know, again times the density of water 1 all over 1 plus E. So meaning that in here we are supposed to find our saturated, we are supposed to find our void ratio, which is E. Now, the void ratio is given as E. So I'm going to calculate the void ratio. So the void ratio, I'm going to calculate that from the dry density. We know that we've already calculated for dry density, right? We've calculated for dry density. So I'm going to use the dry density formula. So I know that dry density, again, is equal to the density of water multiplying the specific gravity all over 1 plus E. So in here, I'll use this formula to find my E, right? When I calculated for my dry density, I had 1.33. And this should be equal to the density of water 1 times the specific gravity 2.71. All this divided by 1 plus E. So I just go ahead and cross multiply. We're going to get 1.33 plus 1.33 E should be equal to 2.71. And I can go ahead and make E the subject. Making E the subject, I'm going to get my final answer to be 1.03. Note, void ratio has no units. 1.03. So from here, I can go ahead and substitute my E into this formula to get my saturated density. So my saturated density is simply going to be 2.71 multiplying 1 plus 1.03 by 1. All this divided by 1 plus 1.03. Then I'll be getting my saturated density to be 1.842. So 1.842 gram per centimeter cube. Right. The next thing I'm supposed to find is my porosity. Porosity. And my porosity is simply represented as M. And that's simply E over E plus 1, which is the void ratio over the void ratio plus 1. The void ratio is given as the void ratio is given at 1.03. So we have 1.03 divided by 1.03 plus 1. Then we have our porosity to be 0.507, and which can be represented as a percentage. So we multiply by 100%, that gives 50.7%. Now, the last thing we're supposed to calculate in this question is to find our degree of saturation. So let me clear this side. We are supposed to find our degree of saturation. So first do that. So the degree of saturation is given as the volume of water over the volume of void, which is also the water content that multiplying the specific gravity all over the void ratio. So we are going to simply get our Water content we calculated, we had 0.375, which you convert to 37.5%. Now know that anytime you are using the water content in calculation, you should use the decimal figure and not the percentage figure. So here we are going to have 0.375 times the specific gravity all over the void ratio, which is 1.03. Then we have our degree of saturation to be 0.987. Again, we can convert this to percentage, and we have 98.7%. Yeah. So this question on one question on under phase diagrams, if you take notes of. I'm going to take the second question under phase diagram. Let's take the second question under phase diagram. Now, in this question, the question says, so this is going to be our second question. A natural sand deposit with water contents of 13%. So water content has been given in the question. We have water content W as 13%, which we know that since I said we don't work in what we don't work the water content when we are solving water problems related to water content, we convert the percentage to decimal. So in this case, we have a 0.13. Let's continue. And has a bulk density of 1.8. So we've been given bulk density. We've been given bulk density, which is rho B, as 1.8 gram per centimeter cube. Now, we've been asked to, okay, we've also been given the minimum dry density of the soil. So minimum dry density, which we also represented as. So rho D min is also giving us 1.50 grams per centimeter cube. We've been given the maximum dry density as well. So maximum dry density. We've been given the maximum dry density, which is also MD max, as 1.73 grams per centimeter cube. So a natural sand deposit with water content of 13% has a bulk density of 1.8 grams per centimeter cube, minimum dry density of 1.50 grams per centimeter cube, and maximum dry density of 1.73 grams per centimeter cube. Now the question is determine the degree of denseness of the soil. That's the question. So let me write that one. We have to determine the degree of denseness of the soil. The degree of denseness of the soil. Right. So now this also, and just as I said, phase relation is just formula work. So the degree of denseness represented as dr is giving us the maximum is giving us the maximum dry density. The maximum dry density multiplying the dry density minus the minimum dry density. All this divided by the dry density multiplying the maximum dry density minus the minimum dry density expressed as a percentage. Yeah. So this is the formula we're going to use. But you realize that we have everything. Our maximum dry density is 1.73. Minimum we have 1.50. But we do not know our dry density, meaning that we have to go ahead and find our dry density. But we know that our dry density, it's simply bulk density over 1 plus water content. So our bulk density was given in the question as 1.8, and our water content was given as 1.13. So in here we can find our dry density, which is 1.59 grams per centimeter cube. Then we can go ahead and substitute this everything into the equation. So what's our dry mass? That's 1.73. So we have 1.73 multiplying 1.59 minus the min. What's the min? The min is 1.50. All this divided by the dry density, 1.59. Again, multiplying the max, which is 1.73 minus 1.5. All this expressed as a percentage. So when you point this into your calculator, you'll be getting your dry density, your degree of denseness to be 42.58 degrees. Yeah. So this is also one constant under phase relation you are supposed to take note of. These are questions, these are questions from your slides, and also some questions we remember during our time. So take note of them. So I remember there was this question on compaction. They're supposed to, okay. So I think effects of soil compaction. What are some of the effects of soil compaction? So when you did your compaction exercise, the main aim of the compaction exercise was to reduce soil permeability. That's one. So we are reducing. So when we perform compaction, we reduce soil permeability. Reduce soil permeability. We increase soil strength. So we increase the shear strength of the soil. So increase shear strength. Again, compaction reduces compressibility. Compaction reduces compressibility. Then also it reduces the level of erosion. Reduces the level of erosion. And it reduces liquefaction potential. So take note of this. Reduces liquefaction potential. Right. So these are effects of soil compaction. Effects of soil compaction. Good. Now, let's proceed. What do we have again? I don't know if I should go ahead and solve this one. No, I can't. I think I've already solved the question on this one and this one. All right. So, let me check. Again, there was a question under more column where we were asked to draw diagram. We should draw and label a diagram that, draw and label a diagram for a loose and then a dense. Yeah, so you are supposed to draw a stress strain graph. Label a stress strain graph for a loose sand and a dense sand. I don't remember if it was mid-sem or was end of sem. So a stress strain graph. So you simply have this as, so over here we have our strain, then we have our stress strain graph. So we are going to do for normally consolidated or loose sand. So normally consolidated the same as loose sand. So this is for loose sand, right? Loose sand. or normally consolidated. So now, for a loose sand or normally consolidated sand, the stress strain graph looks like this, where it has an ultimate stress. Yeah, so this is basically how it looks like. Then when we come to that of the dense sand, the dense sand also over consolidated soil. The dense sand also known as over consolidated soil. The stress strain graph is simply going, so we have strain and we have stress. Yeah. So with this, the stress strain graph is going to be linear at a point, then it will have a peak, then it comes at some. So over here we have the, the peak strength, then we have the residual strength. The residual strength. This is the stress strain graph for dense sand and loose sand. Now let's do a compaction. So compaction. The result question on particle size distribution. But okay, since I've already started talking about mole column, now we let's assume we've been given a graph where you know that for the mole column there is a portion that you'll be dealing with shear strength parameters. And you know that the shear strength parameters are T and phi. These are the shear strength parameters. These are basic MCQs questions. Take note, shear strength parameters. If they add anything to it, that thing is not a shear strength parameter. These things are shear strength parameters, C and phi. Whether C or C prime, phi or phi prime. Yeah, the shear strength parameters. So where this is cohesion and this is angle of friction. Take note. These are the shear strength parameters. If they add anything to it, it's not a shear strength parameter. Now, you can be also be given a graph where you'll be asked to determine the shear strength parameters of the graph. So over here, let me just draw a basic graph. So let me just say this is a graph. The line will be plotted on the graph this way, right? Then we'll name it this side as normal stress. Then, yeah, normal stress. But then what's supposed to be? But this side also. But let's give it parameters. So let's say here it is 10, 20, 30, 40, 50. Again, let me say 10, 20, 30, 40. Right. So this is the shear stress. Okay, this side is the shear stress. Yeah, so shear stress against normal stress. This figure shows a shear stress versus a normal stress plot from a direct shear test. Basically something like this. Then you'll be asked to determine the shear strength parameters from this graph. The shear strength parameters from this graph. This is the easy. Simply what you're going to do is you get a ruler and a pencil, then you extend this line to intercept the vertical axis. The point at which you intercept the vertical axis is your cohesion. Oh, the point at which you intercept the vertical axis is your cohesion. So in here, my cohesion is simply going to be, let me say, 18 kilonewton per meter square. Right. So what you are just basically going to do is to extend this line to tap like you extend it to touch. Then you read off the value at that point. Good. Now you are supposed also, since this is shear strength parameters, we've already find the cohesion. You are supposed to find the angle of friction as well. Now to find the angle of friction, you just draw a vertical line, a horizontal line here, this way. At the point where this line, the extended line met the vertical, you just draw a horizontal line. Then com- with your protractor, you read off the value at the side. So you put your protractor. So let me just, so your protractor is simply going to be on a sample like this with the 0 line or the 90 line here. Then you are going to read from the bottom this way, from this side. So you are going to read off the value over here in degrees. So let's say you have 20, assuming maybe you have 20. So you're going to, let's say, 20 degrees. And that will be your shear strength parameters. Take note of that one. Yeah, so those are questions I jotted down for under more circle. Okay, I think there is one more under one more question under more circle, which I'll come back to later. But for now, let's talk about we talk about compaction. That's question. Alright, so let's deal with particle size distribution first. Let's deal with particle size. Then, so we are going to deal with particle size where we'll talk about the classification schemes. Yeah, we are going to look about two. Then we'll also look at the unified. Yeah, the add two and the unified. Okay. So then I have this here. Don't know if this is playing now, but there with me. So we have this. We are going to use this graph. Yes, we are going to use this graph in our classification. We're going to use this in our classification now. The particle size. This is a particle size distribution curve. Just as we all know, this is a particle size distribution curve. And basically, there are certain things you'll be asked to do. You'll be asked to classify the soil based on unified, classify the soil based on ASHTO. You can also be asked to find the coefficient of uniform conformity and all that. Where you find CU, you find CC. Yeah. Some of those are some of the basic things you'll be asked to do. Um, let me cross check something. Okay. So these are basically some of the things you'll be asked to do. Find coefficients of uniformity and all that. CU, CC. We asked to find the activity of the soil, plasticity index of the soil. Then probably you classify the soil. Yeah. Well, let's do that. So we are going to use this particle size. We are going to use this particle size distribution curve. Right. So let's continue. The particle size. All right. So in this question, we've been given our liquid limit. Our liquid limit at 55%. Then we've been given our plastic limit. Our plastic limit as 26%. Yeah, for this particular size distribution. Now we are supposed to find our CU and our CC from this question. CU and CC, of which we know our basic formula work. So you know that CU is basically D60 on D10, and CC is basically D30 squared divided by D60 by D10. But note that this D60, D10, and D30 are known as effective diameters, right? Effective diameters, and they are supposed to be read from the graph. So we are going to find D60, D10, and so D60 simply means the percent finer that passes through the 60 millimeter sieve, right? That passes through, so the percent finer than 60% passing through the diameter. That's what we mean by D60. Then D10 percent finer than 10. Yeah, so percent finer than 10%, right? And percent finer than 30%. So those are effective diameters. So now we are going to read this value. So first, let's start with D10. So we come to our graph. We read from the percent finer aspect. So D10 means 10%. So this is 10%, 10%. Then we simply trace. I think you can. You simply trace. Trace. Let me change the color of the pen so that you could see. So yeah. So this is 10%, right? 10. So we simply trace that to touch the PSD curve. You trace that line to touch the PSD curve. This way. Then you take it down. Then read the value from this side. So this is a logarithm graph, right? So this is 0.01. This is 0.02. 0.0, this is 0.001, 0.002, 0.003. So I'll be having my 10. So I think because it's a spin, I think it touches it somewhere here, right? Yeah. So I have 0.004 on my screen. I have 0.004. So I have D10 to be 0.004. Now D30. Again, I come to the 30 meter. This 30, right? Then I trace it to touch the PSD curve. Then I take it down. Then I read the value from there. So this is 0.1 and this is 0.2. So this is somewhere around 0.12. Somewhere around 0.12. Mind you, they are in millimeters. They are in millimeters. So this is 0.004 millimeters. D30 have 0.12 millimeters. Then now D60, I come to this 60, right? So again, I'm going to trace to hit the curve and I take it down, right? Let me erase this one so that you can see. So this is 0.1, this is 0.2, right? This is 0.2, meaning that this is somewhere 0.3. Right? This line is also 0.3. So my D60 I have 0.3 millimeters. Now I can just go ahead and substitute them into the equation. So to find my CU, I simply have D60, which is 0.3 over my D10. And my D10 is 0.004. So 0.3 over 0.004. And that gives me about, yeah, so we are going to express this as a percentage. So that gives me about 75%, right? Then go ahead and find CC by substituting. I don't want to move further away. I want to do it just here. So we are going to find CC. So you know that CC, it's simply D30 squared. And you know that D30 was 0.12 squared divided by D60, which is 0.3 by D10, and D10 is 0.00, so you have 0.004. And then CC will simply give us what? 12%. 12%. Yeah. So these are the values for CU and CC. Now you could be asked to determine the activity of the clay of the soil whose PSD curve has been drawn. Right. Of the soil whose activity has been. So now to determine the activity of a soil, the activity of a soil is simply giving us the the plasticity index, the plasticity index divided by the clay fraction, right? And the clay fraction is simply the percent finer than the 0.002 millimeter sieve. So the clay fraction is simply percent finer than 0.02 millimeters. The percent finer than the 0.02 millimeters. So I'm going to read that from the graph. So now, first of all, you have to find the plasticity index, right? And that's giving us, so I have my plasticity index is giving us the liquid limit, which is WL, minus the plastic limit, which is WP. And that was given initially. I made mention that our liquid limit is 55% and our plastic limit is 26%. So we are going to have our liquid limit 55 minus 26. And this is simply going to give us 29%. So now we know our plasticity index. We have to find our clay fraction, which I said is the percent finer than the 0.02 millimeter. So let me say our activity of the soil is going to be 29% divided by. So we are going to read the 0.02 millimeters percent finer. So you go back to the graph. Let me read everything on it. Then you read the percent finer than the 0.02 millimeter. So this is 0.01. This is 0.02, right? So you simply, this time around, you trace to the top. So 0.02 means a curve here. And you take it to the percent final line, right? So this is approximately 16%. So now you go back. So we know our percent final than the 0.02 millimeter is about 16%. Then we compute this. We have our activity to be 1.81. 1.81. You can ask comments on the activity. I know that if the activity is greater than 1, the soil has a very high shrink flow potential. So you are going to you can be asked to classify the soil based on the activity. So take note of that one. So it hasn't has a limit because the percent is going to cancel the 2% signs are going to cancel out. All right. Let's move ahead and classify the soils. So we are going to classify the soil based on the Astro classification scheme, and also we classify the soil based on the unified classification. So let's begin with. So let me just go and let me bring back this. Let me bring this back. So that we can write. Let me just put this here. So that we can get a full space anyway. Yeah. Okay. So this is our graph again. We are going to classify the soil based on this graph. So we are going to. So first of all, let's start with the unified classification. Okay, no, let's start with the actual. Let's start with the actual. So there are basic things you should know when you are when you are classifying soils based on the actual classification scheme. The actual classification scheme. You need your percent finer than the 0.07 millimeter sieve. You need your percent finer than finer than your 2 millimeter sieve. Then you need your percent finer than your 0.425. Percent finer than your 0.425 millimeter sieve. These are the three things you need when you are doing astro classification. Right. So let me just show you how the astro classification table looks like. All right, this. Let me take this. It's the right position. It's down the road. So this is how the astro classification scheme looks like. So, this is how it looks like. So it has two sides. It has this side which is the granular materials. And it has this side which is the filled clay material. So we are going to all right. So first of all, you are going to consider the three things I said you need to astro. The percent is finer than the 0.075 millimeters. The percent is finer than the 2 millimeters, and the percent is finer than. And these things are supposed to be read from the ground, right? So first of all, you need the percent finer than the 0.075. So where is 0.075? Let me increase this then so that you can see. So this is 0.001, 0.002, 003, 004, 005, 006. This is 0.007. So 1, 2, 3, 4, 5, 6, 7. So this about 0.007, right? 7. So 7.5 will be somewhere around here. Yeah, somewhere around this side. So 2, 3, 4, 5, 6, 7, 5 will be somewhere around here. They are simply going to trace that to the curve, right? Simply going to trace that to the curve. I think it's quite, yeah. So you are getting something around 0.07. So this is 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07. So 0.075 is somewhere here. Yeah, I think this is the plot. Yeah, so this is 0.075. See how the logarithm scheme can be confusing. So you are supposed to study it very well. Then you trace it to the other side. So you trace it here. Then you read off the value. So that's somewhere approximately 16%. It's 20. So somewhere approximately 24. Yeah, so let's say 24%. So this somewhere around 24%, approximately 24%. That's the percent finer than the 0.075. Percent finer than the 0.075. So I have this to be 24%. Now you read the finer than the 2 millimeter again. So let's come back to our graph. Percent finer than the 2 millimeter. See. So this is 1. This is C. So hit the graph somewhere here. Then you click it to the percent final line, right? Let me use I hit the percent final line. So somewhere around this side. This is approximately 94. So this 90. So this approximately 94%. 94%. So percent final that the 2 millimeter sieve, 94%. Then you go ahead and find which is the percent final and the 0.425 millimeter. 0.425 millimeter sieve. So again, there's 0. We need 0.4. Yeah, 0.425. So there's 0.1, 0.2, 0.3. There's 0.4. So 425 equals somewhere in the middle of this line. Yeah, so I think there's the plot, right? Then you trace that value. When you trace that value, okay, so that's approximately 70%. So we read out the three values we need when we are dealing with H2, right? 70%. So take note of this. We are going to use them. So from there, you move to your classification scheme, your table. So this is the general classification. So I just initially said that the table has two forms, two parts, the granular material aspect and the finer material aspect. So you have to know which aspects you are going to use, right? Which aspect. So you are going to use this aspect, which is the first. So let me name here one, two. You are going to use the first aspect if your percent passing through the 0.075 millimeter sieve is 35% or less. And you are going to this side if the percent passing through the 0.075 sieve is greater than 35%. So you check your 0.075. What value did you get? 24. 24 is less than 35, so meaning that we are going to use 35% or less. So we are going to use the first part of the table. This is the aspects we are going to use where I've named as one, and it ends here, right? It ends here. That's the first part we are going to use. So we are going to use the left side of the table. Now, it has B classification, sieve analysis. This is where you are going to use to name your classification. But the main classification starts from this side, the 2 millimeter sieve, right? It starts from the 2 millimeter sieve. So first you check the 2 millimeter sieve. What percentage bigger? We had 94%. So it starts from the very first box. If it's satisfy the condition in the box, you move down. But if it doesn't, you move forward. So it's satisfied. So in here, the first condition was the 2 millimeter sieve, right? We have 94%. But the maximum over here is 50, and we are having 94, meaning that this condition is not satisfied. So we move on to the next box. But the next box gives a dash, meaning that whatever condition is satisfied. So we are able to satisfy this condition. So after satisfying this condition, we have to move down to the next table, the next box, which is for the 0.425 millimeters. With that one, we have 70%. But the maximum over there is 50 and we have 74. We are unable to satisfy this. In here, we don't move forward this way. You have to go back and move to the next option before you can come down. So we move back. Then in here, still a dash, so we can satisfy this side. Now when we come here, 51 minimum, and we have the 0.475, right, is 70%. And the minimum is 51, meaning that this condition is also satisfied. Then we come down to the 0.075. With that one, we had 24%. So since we have 24%, the maximum over here is 10. And we have 24. This condition is not satisfied. Right. This condition isn't satisfied. So we have to move on to the next. But we can't move on to the next. We have to go back and check if the top also condition satisfied. So now we move here. There's a dash satisfied. This is a dash satisfied. 35 marks, and we have 24. Yeah, so this is also satisfied. Then now we come here. Over here, there is no value, so this is also satisfied. Then the liquid limit. The liquid limit in there. The liquid limit in the question was given as 55%. 55. But our maximum is 40, meaning that this side is also not satisfied. So we have to move here. But we don't just move. We have to check if the top at that side is also satisfied. So this is a dash satisfied. This is a dash satisfied. That's 5 marked. Then the zero, we have 24. So this is also satisfied. This is satisfied. Now the liquid limit is 55. The minimum is 41 here. So satisfied. Now our PI, which is the Plasticity Index, which is the what liquid limit minus the plastic limit that we calculated. 55 minus 26, we had, what did we get? We had 29. But in here, the maximum is 10, not satisfied. So we have to move. But we have to check the remaining top. So here, satisfied, satisfied, satisfied. No, so satisfied. Over here, maximum is 40, but liquid limit, we have 55, not satisfied. So although this side was satisfied, this is not satisfying. So we have to come to the next. So dash satisfied, satisfied. This was maximum of 35, yeah. And this was 24. So satisfied, satisfied. Liquid limit is 55. The minimum here is 41. So satisfied. Now our PI, we had our PI to be 29 and the minimum is 11. So satisfied. So we are done with the classification scheme, right? Then we have to read up our values. So see, so in here you can be asked to classify the soil based on the usual type of significant consequence. Meaning that for this particular soil, the usual type of significance, when we classify the soil based on this box, you say that the soil, so silty or clay, gravel, and sand. So you say that the soil is silty or it's clay, gravel, or it's sand. If you have to classify based on this. If you have to classify based on the general ratings, we say that the soil is excellent to good. So we start from excellent starts from, we say that the soil is good since it's at the extreme end. If we are being asked to classify based on good classification, which is the top, we say that the soil lies under A2, right? But the classification is, since it's at the extreme end, is going to be what? A27. So this particular soil is A27 under the good classification. Yeah. So this is how you read from the ASHTO table. This is how you read from the ASHTO table. Now let's move ahead and classify the same soil based on the unified system. So let me also go for the unified table. Okay. So we're going to classify the soil based on the unified. So you realize that the ASHTO already has two sides of the table. With the unified classification, the tables are not on. We have two different tables. We have the one for the cost and one for the fine. We have one for the cost and one for the fine. It is also the unified classification table that. So this. So in order to, but before that, let's talk about this demonstrate. In order for you to also classify based on the unified classification, in order for us to classify based on it, we also need certain things. Now with that one, so you need your percent finer than 0.075 millimeters. Of which we calculated, we went from the graph and was 24%. You need your percent retained, right? Retained on. Now, your percent retained on 0.075 millimeters. So if you are saying that percent finer than the 0.075 is 24, meaning that the percentage that passed through the 0.075 millimeters is 24, then what percentage will be retained? the percentage retained on this same sieve is going to be just what 100 minus 24, right? 100 minus 24, and that's simply going to give us what? This is going to give us 4%, if I'm not wrong. 66. Oh, this is 76 or something. Yeah, 76. Sorry, this is going to give us 76%. 76%, right? This is the percent retained on the sieve, 76%. Now, you also have to check, you also need your percent passing through the 4.75 millimeter sieve. So percent passing through 4.75 millimeter sieve, right? So we'll go and check that one as well. So let's go to the graph. Then we check the percent passing through the 4.75 millimeter sieve. So this is the graph. 4.75. So this is 2. This 3. This 4. 4.75 will be somewhere in this box. So I think this is the 4.75 plots, right? Then you trace it again to this side. Then you read off the value. So the 4.75 is approximately giving us approximately 98%. It's giving us approximately 98%. So we have that. So 4.75, we have approximately 98%. Now again, right. So since this is the percent finer than the 0.075, so now let's check our graph and let's see what we need. Right. Let's see what we need. So this is the unified classification system. Before you use this sieve, you should know whether the soil you are dealing with is coarse grained or fine grained, right? So let's go down again and make that analysis before we know if the table we are going to use is right. So over here, percent finer than the 0.075 millimeters is 24%, meaning that the material is 24% fine, right? 24% fine, and what? 76% coarse. Material is 76% coarse, right? So since the material is 76% coarse, then we have to use the coarser ones is more than the finer. So we have to use the coarse classification table. So over here you can see, you can Google this graph from online, then you follow along. So over here we have greater greater than or equal to 50% retained on the number 200 sieve. And the number 200 sieve is simply the 0.075 millimeter sieve, right? And we have 76%, which is greater than 50. So we can go ahead and use this classification table now. So since the first condition has been satisfied, so let me erase there. We have 70 over here. We have 76%. So the first condition has been satisfied. Now we branch to this side and this side. Which side are we going to use? Are we going to use the sand? This percent, this side is if the percent of gravel is greater than the percent of sand. And the bottom aspect is if the percent of sand is greater than the percent of gravel. Meaning that you have to calculate that as well. You have to know the percent of sand and the percent of gravel. Now, if you want to know the percent passing through the percent of the gravel, right? That's when the 4.75 millimeter sieve comes in. So retained on the percentage that is retained, the percentage that passes through the 4.75 sieve will be sand, and the one that will be retained on it will be coarse. So this is a combination. So for this particular aspect, this 98%, right? Meaning that 98% passed through the 4.75 millimeter sieve. And since it's passed through the 4.7 millimeter sieve, we consider that as sand. And if you want that for gravel, gravel is simply going to be out of 100, so 2%. So meaning that there is more sand particles, there are more sand particles than gravels. So over here again, we come back to our classification scheme. So which side are we going to use? We have 98% sand, 2% gravel. So meaning that we're going to use this side of the classification scheme. We're going to use this side, right? So we don't go here. So meaning that we are going to move down here since sand percent is more than gravel, right? Now over here we have three parts. One, two, three. Which side are we going to? They are all talking about fines. And the fines is simply the 0.075 passing through, the one that passes through. And we have 24%. So what's which this is less than 5%, 5 to 12, this is greater than 12. So meaning and we have 24, meaning that over here too we go down this way. Now when we get here, we have three of them. So over here, you are going to read from the Unified Classification System of Fine Grained Soils. You are going to read from this chart, the Casagrande Plasticity chart. That's where you are going to read those values. You need to know your where the soil will fall on this ground, right? So the soil has a PI aspect and it has a liquid limit aspect and it has an A line. It has an A line. So you are going to use this the formula for the A line. You're going to put in your values, right? So we had our so the A line. So you find your PI to know whether the you find your PI using this formula, then you compare to your PI to see whether the value or the soil will plot above the A line or below the A line. So the PI value is simply 0.73 multiplying what the liquid limit minus 20. This is the formula, right? And initially, when we calculated our PI, I think we had 16, we have 29%. Yes, when we calculated our PI, we had 29%, which was 55 minus 26. We had that. Now, let's go ahead and solve. So we have 0.73 multiplying our liquid limit. Our liquid limit was given as 55 minus 20. So minus 20. Then when we compute this, so we are going to check if our this is going to slot above the A line or below the A line. So 0.73 multiplying 55 minus 20. And that's giving us 20, that's also giving us 26%, right? So we are going to, our value is 20, we are getting 25.55, which is simply approximately 26. So meaning that our soil will plot above the A line. We had 25, 26, 26. Where is it? We have 26%. And the value we calculated for is 29. The value that we calculated for initially was 29. And the value we have here is 26, right? What this means is that our value will plot above there, will plot above there. All right. So it's going to simply plot above the A line, right? So let's trace. Our liquid limit in the question was given as 55, and our PI we calculated initially was 29. We are not going to use this. This was just a test. We are going to use the one from the question, which was 55 minus 26, liquid limit minus plastic limit. So we are simply going to trace. So 55, we have 55 somewhere here, right? 55 somewhere here. Then 29, this 20, so 29 will be somewhere here, right? So realize that they plot above there. So they meet somewhere here, okay? and it's above the A line. And it's above the A line. So this chamber one, chamber two. It's in the second chamber. You realize this is divided by this line. It's in the second chamber. And in the second chamber too, it's above the A line, which is a classification with CH, right? CH. So you go back to your graph, then you confirm. So now we were here, right? We came down here and we are here. So our fine, we had a classification of what CH, CL of CH. So meaning that we are going to go along this line. They are going to classify our soil as SC. We are going to classify our soil as SC, right? So under the unified, our soil is classified as SC. But go do research also and see if this thing will plus about kind of get myself confused a bit. So check if so this is what you've got 29. And this is what you calculated from the A line formula 26, right? To find out if this is more than this, it will plot below, or if this is more than this, or you'll plot above. But still the theory holds. So I assume that it's plotting above, right? So assuming that it was supposed to plot below, meaning that I'm going to get MH and OH. So when I come to my graph, my table MH of OH, so which is somewhere this. So meaning that I was supposed to use this, then I'll be getting what SM as a classification. So we'll go and find out whether it's going to be SM or SC. Check that one too. Let's move on to the next one. That's how to read from the Astro classification as well as the unified classification. So we are going to take this our last one question compaction. Last we have two more questions to go. One on compaction and one on mole circle. So compaction and mole circle. So let's start with the compaction aspects first. Let's start with the compaction aspects first. So I have a question. I think I came across a question. Right. So where is that question? Yeah. So we are going to work with this compaction question. We're going to work with this compaction question. We will be done soon. So we are going to work with this compaction question. Let's just take notes of it. Right. I think it's clear now. Okay. So this is a result. This is from a standard total compaction test. And you are supposed to fill the table, then you draw a compaction curve. So yeah, for this particular question. Now, let's go ahead and fill the table. So this seems a very simple mathematics, very simple mathematics, like very, very basic that you supposed to do. So this aspect is the mass of wet sample. Now, from here, you have mass of mold plus wet sample. So let's say mass of mold plus what? The wet sample, right? Then I have the mass of, this is the mass of mold plus wet sample. And I have the mass of the mold. So when I simply subtract the mass of the mold, I get that of the wet sample. So in this aspect, I'm simply going to subtract mass of mold. I'm subtracting the mass of the wet sample from the mass of the mold plus wet sample to get my mass of wet sample. I'll just subtract my mass of the mold from the mass of the mold plus wet sample to get the mass of just the wet sample. Like this just goes for this. Then are remaining, you'll be left with this, right? So this aspect is simply going to be 5864 minus 4226. So since the mass of the mold is constant throughout, we are simply so over here it's just going to be this minus this minus this. So this minus this minus that, just like that. So let's go. So first one we have 5864 minus 4226, and that gives 1638. Then we have 98 minus 4226. That gives 1872. Then 6144 minus the same 4226. That gives 1918. This gives 1912. And this gives 1831. Now we have to find bulk density. Bulk density is simply giving us the mass of the wet sample over the volume. So bulk density is the mass of wet sample over the volume. And the volume has already been given as 944 centimeter cube. So we have 944 centimeter cube. So meaning that if I want to find my bulk density, I just divide this mass of wet sample over the volume. So the mass of wet sample for the trial number 1 is simply going to be 1638 over 944 over 944. And that's simply going to be 1.74. Then for this one, it's going to be 1872 over the same 944. So we have 1.98, then 2.03, 2.03 here as well, then 1.94. Then I have to find dry density, right? So you have to find the dry density. You know that dry density is simply the bulk density over 1 plus water content. But you don't know your water content, right? So dry density is simply the bulk density over 1 plus water content. You've already found the bulk density here. You now need your water content. So we go to the second aspect of the table. Let's complete the second aspect of the table as well. Then I think we can go ahead and find. So here too, we are supposed to find the mass of the water. Now we know the mass of container plus wet sample, and we know the mass of the container plus dry sample. What differs between these two is water added to this aspect, right? So if I subtract mass of container plus dry soil from mass of container plus wet soil, I'm going to get the mass of the water, because I can see that the mass, this aspect is simply mass of container plus dry soil plus water, right? So I'm just going to subtract the two to get my mass of water. So this aspect here for container 1 is simply going to, the mass of water is simply going to be 82.1 minus 73.6, 89.6 minus 77.8. So in this table, the mass of water, I have 8.5, then I have 11.8, then 9.5, 10.2, then 12.7. Then the mass of the dry soil, the mass of dry soil. So now I have mass of container plus dry soil here. I know the mass of the container as well. I know the mass of container plus dry soil. Then I simply subtract the container from this. I'll get the mass of the dry soil. Meaning that the mass of the dry soil in this column is simply going to be this as so 73.6 minus 26.4, 77.8 minus 21.8. So over here, which is 73.6 minus 26.4, I'll be getting my mass of dry soil to be 47.2, 56, 40.8, 42.6, 48.4. Then I have to go ahead and find my water content. So I'm going to create another column here, one all for my water content, right? But this water content is in decimals, and this water content will be in percentage. Okay. So now, water content. You know that your water content simply the mass of water divided by the mass of dry soil. Yeah, mass of dry soil. So now you know your mass of water. This is your mass, the mass is for the water. You know the mass of the dry soil. So you're simply going to divide. So the first one you have 8.5 divided by 47.2, 11.8 divided by 56. So you're simply going to fill. So here you have 0.18, 0.21, 0.23, 0.24, and 0.26. Then you just convert them to percentage. So I have 18%, 21%, 23%, 24%, and 26%. Now I'm left with one last factor, which is the dry density. Right. So just as I said, the dry density is the bulk density over 1 plus water content. Right? So for the first aspect, your dry density for container 1 is simply going to be your bulk density is 1.74 divided by 1 plus water content, which is we're going to use the decimal one, so 0.18. That's for the first one. And it's going to give us 1.47. Now for container 2, we have our dry density to be our bulk density, which is this one. So 1.98 divided by 1 plus water content, which is 0.21. Then we'll 1.64. So we have 1.64 here. Over here we have 1.65, 1.64, and 1.5. There is one way you can check whether what you are doing is right. Your dry density, so since it's going to be a compaction curve, your dry density should increase at a point and decrease at a point. You realize that this is 0.47 to 64 increase, 64 to 65 increase. Then it's then decreased at this side as well. So 65 to 64 decrease, 64 to 54 decrease. So it increases at a point and decreases at a point, right? So we are going to draw the compaction curve. Now, to draw the compaction curve, you need your dry density and your water content. Your dry density and your water content. Now, your water content, we are going to use the percentage one in plotting the graph. In plotting the graph, use the percentage one, but in calculating, use the decimal. We are going to plot a graph of dry density against water content. So take note of these values. That's what we are going to use to plot the graph. So a graph of dry density against water content. So I simply have, I don't have a graph sheet, so a graph of, it is dry density, a graph of dry density. Dry density in gram per centimeter cube against water content. And water content is in percentage. Then you label, so you're going to label your field, right? So at this same point, I'll be having two labels. For this water content aspect, I'm going to start, because of my values, I'll start from 16, then 18, interval of 2, 20, then 24, then 26, 28. Let me keep it at let me keep it at 30. Then at the bulk density aspect, the dry density aspect, again, at the same side, for the vertical, I have 1, then I have 1.1, 1.2, 1.3, 1.4, 1.5. This is not a graph, so I'm just showing you a sketch of how to do it. 1.6, then 1.7. All right, so 1.7. Okay, so let's go ahead and plot. So for the first one, we are going to plot so dry density against water content. So the first one we have 1.47 against 18%. So this 18, 1.47 will be somewhere here against 18, which is somewhere here. So I'm going to get the graph to be lying somewhere here. For the next set, we have 1.64 against 21. So 1.64 against this. So this 1.664 somewhere here. Then against 21, this is 20. 21, let's say somewhere around this side. So they meet somewhere here. Okay, let me. For the next set, we have 1.65 against 23. So this 6.5 will be a little bit about 6.4 against 23. So somewhere about this side. The next set, 1.64 against 24. This 24. 1.64 somewhere. Cool. We have this. Then for the last set, 1.54 against 26. This 26. This 1.5. 1.54 somewhere against 20. Then since the compaction curve, you draw a curve to pass through the lines. So you'll be having uh you'll be having something like this. Yeah, a curve. Don't mind my curve. So you're having something like this as the compaction curve. Yeah, something like this as a compaction curve. Now you're not done. You can be asked to find in after even if you are not asked, you're supposed to find because that's the most necessary parameter. Your OMC, which is the optimum dry density, and your MDD, which is your maximum dry density. So your optimum moisture content, which is OMC, optimum moisture content, is found on the quarter content line at the peak. So over if this is the peak, you just trace a line down, then read the value. So this is about let's say 23%. Then again, you do that at this side, you trace it. And this would be about let's say 1.65, meaning that from this sketch, my optimal moisture content is say 23%, and my maximum dry density is say 1.65 gram per centimeter cubed. Yeah, so this is how to go about your compaction questions. This is how to go about your compaction questions. Now let's solve the last question, then we are done with this tutorial. It's going to be on Moore circle, right? So with this particular question, you've been given a table, say, let's say test number, then you have confining stress. You have confining stress. Let's call it sigma 3. We have our deviator stress. Let's call it change in D. Right. Because it's change in sigma D. Then we have our pore water pressure. Let's call it U. Right. So we have several trial test 1, test 2, test 3. Then we have values here. Let's say 155, 305, 505. Then we have 197, 390, 643. Then our pore water we have 50, 149, 64, 244. Yeah. So let's work with this value. We have to draw a Moore circle for the effective stress as well as the total stress. For effective stress as well as total stress. All right. So you have to do some small calculation before you go ahead. So I'm going to simply draw 3 other rows. So row 1, going to draw 3 other rows. And I'm going to use that for my calculation. So 3 other rows. Now, this first row is going to be my sigma 1. Then this one is going to be my sigma 1 prime and my sigma 3 prime. So this sigma 1 is my total stress, right? Yeah. Then this is the effective, and this is the effective for the confining stress. So I have this. So I'm going to just go ahead and compute. So now to find sigma 1 is simply sigma 3 plus the deviator stress, sigma d, sigma d. So now to find the sigma 1 for the first trial, we simply have sigma 3, which is 155 plus the deviatoric stress, which is 197. And this gives us 352. So over here we have 352. Then again for test 2, we have our sigma 1 to be sigma 3, which is 305, plus the deviator stress, which is 390. And then simply gives 695. So over here we have 695. Then you do same for this aspect, you have 1148. Right. Now, the next one you are going to do, you are supposed to find sigma 1, sigma 1 prime, right? Which is the effective stress. This effective stress. So now the effective stress we all know again is simply the total stress minus pore water pressure. So this in this case going to be the total stress for 1 minus pore water pressure. So for trial 1, what's the total stress? 352. This 352 minus pore water pressure at that side 50. Then we have what? 302. For trial 2, we are going to get 149. Sorry, the total stress 695. 695 minus 149. So over here, what did we get? We are 302. Over here, you'll be getting 546. Then here, you'll be getting 904. Then you need to find the last one, which is the effective stress for the confining pressure. So the effective stress for the confining pressure, you simply need, so again, sigma prime 3 is simply sigma 3 minus pore water pressure. So sigma 3 for the first trial, which is 155, minus pore water pressure 50. Then you have what? So this for first trial. Then you have 105. So we have 105 here. For second trial, we have what? 305 minus pore water pressure 149. Then we have 156. And for the third trial, we have 505 minus 244. And that gives 261. So we've completed our table. Now we have to draw our graph. In drawing the graph, so you're first going to draw the mole circle for the total stress, then draw the mole circle for the confining, for the effective stress as well. But you're not going to draw them on separate graphs. I'm going to draw them on the same graph. I'm going to draw them on the same graph. Right, same graph. So yeah, you're going to watch them on the same graph. So now this is what you can do. You need to, so we are going to just plot circles, right? We're just going to plot circles. Okay, so you are going to draw a graph. I'm just going to do a sketch. Okay, so if you have a graph, you can just go ahead and practice. Right, so I'm just going to do a graph. So you have your normal stress here. Normal stress. Okay, in kilonewton per meter square. And I think you have your shear stress here. You have confirmed for that. I think you have you should have your shear stress at the side. Okay. So now you plot for the effective. You plot first for the total stress, then now you plot for the effective. So pairing, just like you've been doing in graph work, you have this first one, you have the first set you have for the total. So you have sigma 1 comma sigma 3. So you have Sigma 1, we have 30352. We have 352. Then the confining we have 155. So this is sigma 1, this is sigma 3. But note that we are plotting all of them on the same stress. So because of these values, I'm just going to give my this thing some value. So let me say here is 100, 200, 300, 400, all the way to, let me name 700, 8, 9,000, 1,100. Oh, I can simply go here. Okay. So 1,100. Uh, then I can have I can have 1,200 here. Okay, because of the highest value over your 1,040. Okay. So now I plot all of them. So this is sigma 1, sigma 3. Okay. So now this is what you have to do. You have to first of all find the how do we call it? First of all, find the radius. You find the radius, then you find the center. Okay. You find the radius, then you find the center. So the radius, so first of all, I'll locate sigma 1 and sigma 3. This is my first point, right? So I'll find the radius. The radius is simply sigma 1 minus sigma 3 over 2. Right. So with the first one, I'm going to get 352 minus 155 over 2. Then you get a certain value. That's going to be your radius. Then you have to find the center as well. The center is simply giving us sigma 1 plus sigma 3 over 2. So we have 352 plus 155 over 2. That will be the center. So I'm just going 352 plus 155 divided by 2. So with the center, I have 253.5. So this one I have 253.5 for the center. And for the radius, we have 352 minus 155 divided by 2. We have 98.5 as the radius. So the radius, we have 98.5. So now you locate 253.5. So 253.5 will be somewhere here, right? So you stand here. So now you need a, a compass and a pencil. You need a compass and a pencil. So you locate the center. So you stand here. Then you open a radius of 98.5, right? A radius of 98.5. So you stand here, open a radius of 98.5. Then now you can draw what? An arc. So you stand here, open a radius of that. Then you can now draw an arc. So when I stand here and I draw an arc, you realize that the arc is going to pass it will pass through the 155, is sigma 3, and also the 352. So that arc will simply be somewhere here. Yeah, so let's do something like this for the first one. Then you go ahead and do for the second one. You have to find also with the second one, you have to find the center and the radius. So the center is simply going to be 305 plus 695 divided by 2. That's 500. So you stand on 500, then you open your compass to you find your radius. The radius is simply also 305 minus, sorry, 695 minus 305, again divided by 2, and that's 195. So you stand here, you open 195, then you draw. Well, then you draw an arc. You realize that when you draw an arc, it's simply going to pass through the 505. It's the 305 and the 695. So the 305 is somewhere here. Then you realize that your arc will go somewhere, pass through the 695 this way. Then for the last point, we have the center to be 505 plus 1148 divided by 2. That gives 826.5. Then 826 is somewhere here. So you stand somewhere here, right? Then you find your center, which is 505 plus 1148. Sorry, your radius. So 1148 minus 505. Then divide by 2. You have 321.5. So you stand here open to 321.5 radius. Then you draw an arc. It's supposed to pass through the 505 and the 1148. So it's going to pass through 505 somewhere here. Then 1148 somewhere here. We'll be having something like this for the total stress. And I'm supposed to draw a line, a tangent to this curve. You draw a tangent to the curve, right? Uh, a tangent to the curve. Because it's not straight, I don't know if you'll pass through the origin or it will intercept over here. So when you do that, you are going to know whether it's going to pass through the origin or it's going to intercept. So again, if you are asked to find the position and the C and your phi, your effective your shear stress parameters, you read the value here as your C, then you find your angle as your phi. You get me? Then you go ahead. Yes. But when pass through the origin, meaning that your C is going to be what? 0. So this is for the total stress. Now you plot for the effective stress. But this time around, I'm going to use short dash lines to plot for the effective stress, but with the same idea. So the effective stress is the one with the prime. So you're going to plot this two. So for the first one, for your first one, your point. So if this we are going to do it for the effective 302105. So 302 here, 105 here. So again, you find center. So 302 plus 105 divided by 2. That gives 203.5. So 203.5 will be somewhere around this point, right? Then you find the radius, which is 302 minus 105 divided by 2. That gives 98.5 as well. So you stand here, open 98.5. Then you draw an arc. So that arc is supposed to pass, was going to pass through 105 and 302. But this time I'm going to use short dash lines. So you're going to get something like, let's say you're going to get something like this. Short dash line, right? Then the remaining, so I'm not going to continue for that. Then maybe you get another something like this, right? And another one something like this. Then that one, so you're going to draw a line, right? Then you read those two same values. Well, I don't know. So you when you draw it for, you know whether it will pass through the origin or will not pass through the origin. So this another question: how you go about your mole circles? This aspect of the you go about this aspect of mole circles. Yeah, I think it's come to the end of the presentation. If you have any questions, you can leave it. If you have any question, you can just go ahead and leave it in the comment section. We'll come back and answer them. Or you can leave your messages as well in the Educare group. We'll come and answer them. Or you can also DM any of us if you have any question. Then we'll go ahead and solve it for you. Yeah, but I think I recall some of the MCQs. We're definitely going to have MCQs, but yeah. So I've already stated one of the MCQ questions that I remember. I remember this now. So you can just go ahead. I think you can when you rewatch the video, you remember that. I don't really remember what I said. I have effective search strength parameters. Yes, I think that was one question. And also under compaction, where did we do the compaction? I think there was a question in compaction. This compaction. Now in compaction, you can have we have something we call an air void line. Okay, I think this was an MCQ question. Something we have something we call an air void line. So if I have two compaction curves, let's say this way, and I have an air void line this way, right? The curve that's closer to the compaction curves, right, is the one that's I think it's being compacted more. Something that was how the question was said. So let's say this A, this B. Since A is closer to the air void line, A has a higher, I think, a higher compaction energy. Was it about compaction energy? A higher compaction energy than B. So the one that's more closer. Okay. I think it was about compaction energy. Then we also wrote a report on sheep foot and vibration foot rollers. Sheep foot. And he brought it. I don't know if you guys have done that. Sheep foot and I think vibratory rollers. Yeah, vibration. I don't know if you got. So sheep foot is basically used on sheep foot is basically used on fine grain soils, right? And the vibration is usually used on coarse grain soils. So you can research on that. Yeah, you can research on that as well. Then you check chemical weathering and physical weathering. So when you watch our previous videos, we've already some of the questions, some of the videos we were teaching, especially the introduction, we talked about these things. So check. Um, so chemical weathering is usually in tropical regions, right? Tropical regions, and not arid. Okay, so tropical regions. So you can also check that. And I think this when you come to the same soil, first one I talked about, but you let me just not talk about it. This shrink swell potential stuff. So Montmorillonite has a shrink swell potential comparing that to elite and elite and kyrillite. You know that elite is also known as smectite is also known as Montmorillonite. So check all those things as well. Then I think you'll be fine. We've already done some of the question on how to draw particle size distribution curve. That's why in this tutorial we didn't add anything like that. So you can, if you want to know how to draw, you can simply go back and draw that. Yeah. So I think that will be all. That'll be all. Now from this equation, this is the last thing I want to talk about. I should have said this when we're talking about stress. So from this equation, total stress is equal to effective stress is equal to total stress minus pore water pressure. What this means is that if there is an increase in pore water pressure, then if there is an increase in pore water pressure, then the effective stress is going to what? Is going to decrease. Is going to decrease. Right. And pore water pressure increases if pore water pressure is a function of groundwater, right? So mean that when more water enters the soil, pore water is going to increase. So when let's say rainfall and all that, if when it rains heavily, meaning that the water content in the ground is going to increase, and as that water pressure will increase, which in return, effective stress is going to decrease. Right. So I think this is going to be the end. If you have any question, you can just leave it just as I said, and that way it's all the best in your